All right, in prior videos, we've looked at each of these three models that have all exponential functions in them, and we have just kind of shown some graphs to kind of give an idea about how adjusting the parameters a and b, or the parameters L, A, and K, how those change the shape of the graph. As you can see in this particular logistic model, different values of L, different values of A, different values of K, and we've seen what those graphs move live in Desmos. So the question now is, how does one turn this into a math problem, and how could typical math problems be phrased from them? Okay, so these exponential functions and models are have rather involved functions in them. So maybe to get started, we could look at a typically phrased problem here. And I just want to focus on prior videos where we try to find a formula for the x-coordinate of the critical point. So we're used to finding critical points or critical numbers, and each of these functions over here, we want to find a critical point of the function f. But the fact that all these functions over here have parameters a and b in them, our critical number is going to change as a and b change. So the point of these problems is to see what happens to the critical points. So if we start in number 11 and we look at this function f of x is equal to x minus a squared plus b, right? And this parameter a and b, we know that a and b are going to change the shape of the parabola, right? X squared, the x squared function is going to be some sort of parabola, and a and b change the shape of that, and we know that b is going to move the parabola up and down, and we know that a is going to move the parabola left and right. So how do the parameters a and b change where the the critical point of this function? We know the critical point is going to be a place where the function has a local maximum or a local minimum. And this parabola may be opening upward, it may be opening downward depending on the formula itself. But no matter what, the critical point is where the local maximum or minimum of that function is going to occur. So we could see here that if we want to find where a formula for the critical points, we need to look at the derivative of the function being equal to 0, or when does the derivative does not exist, right? And we can see that the derivative of this function f prime of x is, according to the chain rule, 2 times x minus a times the derivative of the inside function, and then derivative of b, which is a constant, will be 0, and the derivative of x minus a is equal to 1. So we can see that the derivative is 2 times x minus a, which never does not exist. So the only way we have a critical number here is if f prime of x is equal to 0. So that would be 2x minus 2a equaling 0. So x would be equal to 2a divided by 2. So x is equal to a. So whatever the value of a is what our critical number is going to be. Okay? And we can see that that will kind of make sense when we look at the functions and the parameters in Desmos. So let's bring Desmos up now, wherever that was. Sorry, let me bring my internet back in. Let's bring up Desmos, and we'll get rid of our old model, right? And our new model was f of x is equal to x minus a squared plus b. And if we add a slider for all a and b, right, we can see that no matter what a and b are, right, that this parabola is always going to open upward. And that is because there is a 1 in front here. So that 1 will make sure the parabola is always opening upward, because 1 is always positive. And A, we can see A is shifting the left and right position of the parabola. Excuse me. And B is controlling the up and down. Okay. So we can see that even though the parabola B is moving the parabola up and down, it is not changing the location of where the critical number is. It's not changing where this function parabola has a local minimum. This function will always have a local minimum, and that local minimum is going to change with x is equal to a. So here we can see that when a is equal to 2, our local minimum is at 2, a value of x, and when a becomes 4, our local minimum is at the same value of a. And that is what we saw mathematically. Okay, so if we look at another function, okay, let's take a look at the x cubed minus ax squared plus b function. We can see what happens here. Let me insert a duplicate page, edit, copy. Done. Let me insert that page again, and we can move on and see what happens in a new example. Okay, so similar problem. Okay. We want to look and see what happens to this function. Now it's a function with two parameters. F of x is equal to x cubed minus ax squared plus b. Okay, so if we want to look and see how does the critical point change, we need to look at the derivative, which is 3x squared minus 2ax. The derivative of b is equal to 0. We can see that f prime of x is equal to 0 when x, we get to factor out the x, when 3x minus 2a is equal to 0. So this will happen at x is equal to 0, or x will be equal to 2a over 3. Okay? So what we're going to see here is that if we look at the sign line for f prime, that we have a critical number at 0 and a critical number at 2a over 3. Okay? So we can see here that checking the test points, if you take a number x less than 0, this will be negative. Okay. If we assume that a is a positive number, then negative 2a is going to be a negative number. And when x is negative, this will also be a negative. So the whole result will be negative, no matter the value of a, so long as a is positive. Okay, so if x is between 0 and 2a over 3, okay, we need to reevaluate, whoops, sorry, that eraser is too big. We need to evaluate our pluses and minus signs. Okay, we need to say that when x is between 0 and 2a over 3, that means that x is going to be a positive number so long as a is positive. So x will be positive. And this quantity right here, 3x minus 2a, right? If x is less than 2a over 3, right? And x is also a positive number, right? Then we will see that 3 minus 2a has to be a number that is positive. And when x is bigger than 2a over 3, right, the two let me see, does that make sense? If x is less than, no, when x is less than 2a over 3, right, that means that 2a will be bigger, so you'll get a negative sign here, and when x is bigger than 2a over 3, you'll have a positive sign. So what this will say is that our function is, no matter the value of a, is going to be decreasing and then increasing again. Let's see if this makes sense in terms of our function, and we can see that we should have a local minimum at x is equal to 2a over 3. Okay? And nothing will happen at x is equal to 0. Okay? So let's take a look at this function. We will get x cubed minus a times x squared plus b. Okay. And let's see, we are seeing, right, at 2a over 3, so for example, let's let x be equal to 1, right? And b be equal to whatever it was, okay? So, it looks like I'm having... Oh, I'm sorry, let's see. I'm sorry, let me go back here. I made a small mistake here that when x was less than 0, we got a negative times a negative, which made a positive. Okay, so yeah, I'm sorry about that. And what we're seeing now is that our function goes from increasing to decreasing, so we have a local maximum, okay, and then we have a local minimum. Okay. So I think what we're seeing in this picture is exactly what we found here, that no matter the value of a, right, no matter what a was and no matter what b was not part of our critical point formula. Our critical point formula was x was equal to 2a over 3. So our critical point was 0 and 2a over 3. A was the only thing affecting that. So this is what we're seeing in this graph, that b is only moving the function up and down. It doesn't change the location of our maximum and minimum. But a does change where the maximum and minimum occur. But it doesn't change the fact that we're going to have a maximum at 0 and a minimum at 2a over 3. Okay? So for example, we can see that if a is equal to 1, right here at 2a over 3, which is 0.6 repeating, at 0.5, 0.6, right here we have a 2a over 3 at 0.6667. We have a local minimum, and at a equals 0, we have a local maximum. And if we go to a being equal to 3, for example, our critical number 2a over 3, if a is equal to 3, our critical number should then occur at 2. Okay, so when a is equal to 3, can you see we now have a critical number? It's still a local minimum because that's what the sign line said. And at a is equal to 2, when a is equal to 3, we have a critical number at 2 times 3 over 3, which is 2. And we still have a local maximum at 0. Okay? And so no matter what a and b are, we're going to have a local maximum at 0 and a local minimum at 2a over 3. So if a became equal to 4, right, if a were equal to 4, for example, we would have, let's say a equals 6. Then we would have a minimum at 12 over 3, which is 4. So if a were equal to 6, we would have a local minimum. I need to zoom out now. That local minimum would occur at x is equal to 4, which is what we are seeing right here. Here's 5, so 4 is this bar right here, and that is exactly where our local minimum occurs, at that value of 4. All right, so that is two straightforward examples of functions that do not involve exponentials, but are just polynomial functions that have two parameters, and we can try to track the local minimum and maximum through its critical points for different values of A and B.